Yeah, of course. Yeah.
Okay. Well, welcome everybody. So I'm Stephen Sakula. I'm the department chair in physics. And let me begin by welcoming all of you to the first event in the SMU physics department speaker series for fall 2020. This is intended as a general interest colloquium, and it's kicking off a month of presentations on the theme Computing the Cosmos. And we're going to begin today with a talk on real-time modeling of the COVID-19 pandemic, which is obviously a timely and very interesting subject, although maybe we're all getting very sick of it, but nonetheless, I think science can provide a lot of interesting insights. And our speaker today is Dr. Daniel Coombs, who'll give us, I think, a bunch of insights into this. He's a professor of mathematics at the University of British Columbia, and I'll give his bio in a second, but I just wanted to remind everybody that, first of all, if you're in our Zoom audience, then in order to ask a question, you have to type the word speak in the chat window. And at an appropriate break point, probably at the beginning of the next slide or something like that, I'll interrupt Dan and then we'll unmute your mic so you can ask your question. Q&A at the end will also, of course, happen. So you can save your question until the end. The presentation should be about 50 minutes long. But you'll only be able to speak when called upon by a host or moderator. And that's so we can kind of control the chaos of all this virtual meeting stuff. And this event is being recorded and simultaneously live streamed on YouTube. So let me introduce our speaker today. So Dr. Daniel Coombs obtained his Master of Science and PhD in Applied Mathematics from the University of Arizona. He did postdoctoral work in theoretical biology and biophysics at Los Alamos National Laboratory before joining the Department of Mathematics at the University of British Columbia, UBC, as a faculty member in 2003. Dr. Coombs contributes to our understanding of health sciences, especially immunology, within host infection, and epidemiology, through the development and application of mathematical, computational, and statistical models. He works closely with experimental scientists at UBC and the British Columbia Children's Hospital Research Center and public health experts at the BC Centre for Disease Control. And Dr. Coombs is a member of the Canadian Chief Science Advisor's expert panel on COVID-19. So without further ado, welcome. Thank you very much for agreeing to give this opening colloquium for the season, and I'll turn it over to you.
Great. And thanks so much for the invitation to speak. It's a real pleasure to be here. This is the sort of first general talk I've given in quite a while, and hopefully things will go okay. I probably have too many slides as a result, and so somewhere I'm going to have to speed up or cut something out. And also before I get started, I just want to acknowledge the real team nature of this project. You know, no one in the world, well, okay, me, I'm not an expert in pandemic modeling, but I think I've improved a bit over the last few months, as a lot of people have, but that's been with the benefit of great collaborations with some of my students, Rebecca and Sarafa, people at Ministry of Health, the BC Centre for Disease Control, Caroline Kaline, especially at Simon Fraser University, which is the other big university here in Vancouver. It turns out that people that study fish know a lot about modeling with uncertainty because they don't get to see the fish very often. And so they're really experts on how to do the kind of statistics you need when you have really uncertain data. And then also colleagues at BC Children's and around the US as well. I'm really happy to be joining you today from the lower floor of my house in rainy Vancouver. It's been raining. It's about 18 or 19 degrees right now. So I suspect in Dallas it's probably 100 degrees Fahrenheit, and you guys are in a rather different place. Okay, so regain control of my computer. Oh my goodness. Okay, well, something happened. I'm going to talk about hopefully sort of 6 different topics. The first one is sort of a recap about what happened at the beginning of this year with the coronavirus. The second thing is sort of a very brief version of things that I teach when I teach advanced undergrad epidemiology, and how maybe we can start to use those kinds of models and tools to build a picture of what's going on with the virus, even now when we're some ways off, and we know a lot of things that go beyond those simple models. I'll briefly present the social distancing model that we developed in BC, which has been used reasonably successfully to sort of project what might happen under different policy changes, and it routinely gets shown by public health by our chief public health officer here. In every 2 weeks, the model gets wheeled out and predictions get shown. I wanted to talk a bit more about herd immunity. I don't know how much time I'll have or how much you've heard about this, but the whole topic of herd immunity is really topical right now. There's a lot of debate in the field about whether any communities may have reached that threshold, and how that will impact policy going forward. So I'll try to speak a little bit to that. I'm not going to tell you the answer because I don't know the answer. And then with the heterogeneous models, so not everybody is the same, this is the kind of tool that we need to do other things in the epidemic. So for example, vaccines are coming, and trying to project some things about the vaccines in terms of deployment, and if the efficacy of the vaccine is not perfect. And that's something we're working on quite actively at the moment. And then some challenges and some summary. And I'm really happy to take questions throughout. It may slow me down a bit, but that's fine. The point of this is for me to say some stuff and you to listen and hopefully learn a few things. And it'll work better if it's a little bit dynamic. And then also I won't feel like I'm shouting into the void for 45 minutes, which I sometimes do.
In the spirit of things, Dan, we're not seeing your slides change if you've been changing them.
I have not changed. I've just been.
Oh, great. Okay, you're just on message.
Oh,
okay.
No, I just was on slide 2, and now, can you see it? Can you see a different slide now?
No, we're still seeing the title slide, weirdly enough.
Okay, yeah, I have it. Okay, here we go. Stop share, reshare, thank you.
No problem. I know there's a funny interaction between Mac desktop and Zoom. So
I lose my mouse. That's the problem. I lose my mouse. Okay, so now you should see a 1 through 6 list.
Yes.
Yes. Okay. I will try to. Do you still see that?
Yes.
Okay. All right. Okay. So the first thing I promised was January 2020. There's a little bit of prehistory before that, though. Even before.
Sorry, Dan. Sorry to interrupt again. It didn't change the slide again.
Oh, good grief.
Maybe just stay in that preview.
Yeah.
Unless you have something specific that's animated on the slide.
No, I don't. If you guys are okay with this, it'll actually make my life easier because I can see my mouse and stuff as well.
Let's do that.
Yeah, let's do that. Great. Thank you. There were 4 coronaviruses circulating in the US before the now famous coronavirus. And in fact, there was a study in 2018, and it was a fairly large multi-center study in the US, and around 12% of people who had influenza-like illness actually had a coronavirus. So these things have presumably been circulating, and we don't know too much about them. But the bottom line of that study was that they're not particularly virulent. There was 1 total day of hospitalization of patients who actually had one of those preceding 4 coronavirus infections. There's not much else. I mean, we know they're around, they exist, they don't seem to do too much. Is that reason because they've evolved to not cause too much sickness and to transmit? Is it because large numbers of us have some pre-existing immunity? No one really knows. We'll probably find out a lot more in the years to come. Then there's the 2 famous coronaviruses that were around before this year. One is Middle East respiratory syndrome, which is essentially a bat camel virus, and occasionally you get human-to-human transmission. There's been 1 large outbreak in South Korea in 2015. It has a very high case fatality rate of 30 to 40%. That's extremely high for any human disease. And then there's SARS, which I remember just when I was moving to Canada was towards the end of the SARS outbreak. And this was pretty big. There were 8,000 cases. It spread from Southeast Asia. It came to Canada. There were 250 cases here just before I moved up here. It had, again, a high case fatality rate. So the current epidemic, it seems to be more transmissible and less virulent, for example, than SARS, and substantially more transmissible and less virulent than MERS. But possibly definitely more virulent than the other coronaviruses. Okay, so let's go back now, cast our minds back to January 31st of this year. And this is essentially a picture of the epidemic at that point. The epidemic, as we all know, had started in Wuhan, which is a city in Hubei province in central China. But by January 31st, we'd already seen cases spreading around the world. There were a reasonable number of cases in Europe, in Middle East, in Australia. In North America, there had been a number of cases detected. If I remember correctly, the first detected case in North America was actually in Washington State. And then there had been cases detected in BC and Ontario. But there had been a month of spread in Wuhan. There had already been over 5,000 some cases confirmed and 42 deaths in Hubei province. This is how we knew this was an issue. I'm sorry that lower picture is not showing up, but essentially all this was showing is in the upper picture in December, there were small numbers of cases and whether they would link to this famous seafood market or not. And then the lower right was essentially just going to show the red bars there, which are a little off center, was supposed to show the development of cases in Wuhan over January. But this data is also available like on Wikipedia. So I accessed Wikipedia right around the end of January. And if you look at the yellow bar plot on the left of numbers of cases in China, or on the right side, conveniently on a log plot, and you can see a very clean looking exponential growth from January 16th to January 30th, with a doubling time of about 1.8 days. And on that day, at the end of January, there were over 15,000 suspected cases and over 100,000 people under observation. And I don't think it's giving away anything to say that if I'd given that talk a week later, we would already have seen the numbers of reported cases beginning to level off. It certainly wasn't exponential anymore. And that was the Chinese lockdown, which was starting to have its effect almost by the time I was looking at this. So this is a nice jumping off point, though, to start looking at simple models of epidemic spread. And so, okay, so here comes some concepts and some mathematics. So the most important thing to know about with infectious disease modeling is always the basic reproductive number, which is the famous R0. And if R0 is bigger than 1, then on average, you get exponential growth. And so exponential growth is possible. If R0 is less than 1, then you're guaranteed that your process will become extinct. So the difference between possible and guaranteed is it's always conceivable that the first few cases may not lead to any further transmissions just due to luck, essentially. So if the first few cases are people in a religious sect where they only talk to each other on the weekends and the rest of the time engage in silent prayer, then essentially your disease is likely to go extinct pretty rapidly. Whereas if it's in young people who go out to parties every weekend, then you may well see the exponential growth. And people talk about the R0s for different diseases. So flu is around 1.5. For polio, it's about 6. For SARS, which was about estimated to be around 2.5. The one that's notably different is measles. That's very, very high. If you're going to control an epidemic, you need your R0 to be less than 1. And if you think about the average number of new infections that you're going to cause those in people around you. And so if some of those people have been vaccinated and are not infectable, then this is essentially going to reduce the R0, if you like. So the measles R0 there of 18 is in an unvaccinated setting. So this was estimated in pre-vaccine times. But we know now that if we vaccinate a very high fraction of people, we're able to effectively reduce that number down to an R0 in a vaccinated setting. And this is why it's important that everybody gets their measles shot. With flu, the vaccination target would be a lot lower. That's possibly because most of us have some pre-existing immunity against flu already, so that already reduced the R0. So going on to just a few more comments about R0. R0 is, first of all, dimensionless, and so it contains no time information. So, for example, you could have HIV infection R0 of about 3, but the epidemic would take years to develop, versus if you have a mumps R0 of about 3, then your epidemic is developing on a characteristic time scale of just a few weeks, because the serial interval, which is the time between infection and infecting somebody else, is typically on the order of days to a week there. R0, importantly, reflects the biology, and the biology we tend to look at as being reasonably the same between different people, but it also reflects the society or the community in which the spread is happening. So I wrote 1491 there because I think it's reasonably well established at this point that diseases which had been coexisting one way or another with Europeans when they reached North America, had a devastating effect and presumably very high R-naughts. There are reports of deserted villages, which are now generally believed, I think, to be the explorers were coming behind a very strong epidemic wave that effectively decimated the societies ahead of them. And there's a book called 1491 which talks about this, and it's an interesting read. Also demographics. So you may have heard, for example, that as we know, coronavirus is more dangerous for people who are in over 65, for elderly demographics. So African societies have African countries rather have comparatively young populations. That population pyramid is a little more healthy than ours, and so presumably they should see lower morbidity, mortality from coronavirus than we see in the Western societies. Okay, and then there are norms around contact and countermeasures. I would say one of the reasons that Korea has done well, comparatively speaking, in this pandemic is likely that they have that recent experience of Middle East respiratory syndrome. Okay. And just finally, a point of nomenclature. R0 is usually before the countermeasures have been applied. After the countermeasures, people often use RT or just plain old R. Okay. All right. So let's think about how we're going to estimate this R0 from the incidence data. So this is the kind of data that was available. So we're trying to estimate a dimensionless parameter from, say, an exponentially growing process. So one thing that we're going to need is we're going to need a time scale to do that with. And the appropriate time scale here is the average time, say, between serial infection events. So it's the time between getting infected and infecting somebody else. And of course, this is going to be a distribution. One thing that's nice is to parameterize this, and we can parameterize this using one of the armada of mathematical epidemic models that exists. And I'm just going to talk in detail about a fairly simple one, which you may have heard of, which is the SEIR model, and this abbreviation just tells us that people move from susceptible, they interact with an infectious person, then they enter the exposed class where they're still not infectious, then they move to the infectious class, and then eventually they'll be removed. And removed can either be recovered, or it might mean that they've been moved into quarantine or that they've died. In any case, they don't infect anybody else. There are some assumptions here. So in the exposed class, we have some exponentially distributed period of exposure, and also in the infectious class. You can fix all these things up by moving to an integral differential equation system, and everything I'm about to say works more or less the same, just you'll get the timescales a little bit more accurately. You can also do this discretely, and all of these things are broadly the same. I like differential equations. I think they're a nice way of codifying kind of a set of assumptions, and so we're just going to do that for now. All right. And just one thing here is there's no demographics, so the total population size here is constant. It's a simple matter to modify these equations to include births and immigrations and deaths and things like this. Okay. So if we look at the actual equations, you can see here a mass action kind of assumption, so that people are exiting the S category, the susceptible category, at some rate that's proportional to susceptibles times infectious people. All right, so this is essentially like chemical kinetics. This N here is actually a constant. Okay, so but this gives an interpretation of this term, which is beta naught is some sort of contact rate, and then what fraction of the contacts that an infectious person makes are with a susceptible person. Those are going to be the number of susceptibles divided by the total population. Okay, so this is called the mass action assumption. These people then show up in the exposed class, where they remain for some period with a parameter sigma, and then they move from exposed to infectious, and now they can infect people themselves, and eventually they recover with some rate alpha. And we can actually take this model and look at it on an individual basis. So the model here is essentially that the infectiousness of a person who just moved into the exposed category will grow and then peak on some day, and then decline over, and they'll remain in. So the average infectiousness, or if you not the average. So the distribution of infectiousness of a person who was infected on day 0, who entered the exposed class on day 0, looks something like this, and we can calculate this, and it's a difference of exponential function. Okay, so then this means we can also calculate the R0. So the R0 is just the integral of this function, because this is the sort of infectiousness function for each person. So we integrate this over time, and we get for this model that the R0 is the transmission parameter beta, or beta 0, I put here, divided by alpha. If you like, this is beta 0 times 1 over alpha. 1 over alpha is the mean time that you spend in the infectious category. It's the duration of infectiousness. And that's exactly what you would expect. Okay. Okay, so how do we go from this model to estimating R0? Okay, so we have this cumulative infection data. So, and it looks to be, roughly speaking, exponentially growing. So we can say, well, the cumulative number of infections, J, is some exponential function of time. We can also define the derivative of this. This is the incidence. So the incidence is just dj dt, and that's also going to be an exponential function of time. But also, this incidence is going to be a convolution of that infectiousness kernel, beta, which is the time distribution of infectiousness, times those people who were infected tau time units ago. And then we integrate that over all delays into the past. So this is just a convolution of these two things. So it's quite standard if you're used to looking at it this way, but maybe a little confusing if you're not. But take it from me, that's a good way to do it. And what we can now do is we can plug in this I of t on both sides. This I of t is an exponential function on both sides of this equation. Do a little bit of cancellation, and we get this nice equation, which goes all the way back to Euler, which is just 1 is the integral of the infectiousness kernel with a weighting where R here in the exponential weighting is the exponential growth rate that's observed in the data. Okay. So now we take the Euler-Lotka equation here, and we can plug in the function beta that we calculated for our SEIR model. If we were using a different model, we might have a slightly different function over here, but we plug it in here, do some integration. I can do everything explicitly in this case. And now the critical thing is I have an equation linking the R0 to the exponential growth rate R. And there are two other parameters in here, which are alpha and sigma. And those, if you remember, those are the average delays from infection to becoming infectious, and from becoming infectious to not being infectious anymore. So we sort of managed to parameterize this. So way back on January 31st, a couple of groups out of China were publishing estimates of R0 based on exactly this kind of data, either from Wuhan or from all of China. And you can see they were sort of reasonably close, depending on which data sets they were using. How did they get those two additional parameters? Well, they said this is a coronavirus, it's related to SARS 2002. We'll just use those as estimates. And then the second group, Liu et al., these are probably papers now, I've just been too lazy to look them up. But the second group also estimated the incubation period for the disease as well, and said it was broadly comparable to SARS. And there were a number of groups doing this through January and February. Okay. But if you like the SEIR model, then you can use it to predict. So Liu and, sorry, those two groups, Liu and Zhao, were basically just looking at the very early phases of exponential growth here, which is what you expect from this model, that it'll be approximately exponential in the beginning. But you can then, once you've got this parameterized, you can numerically run this forward in time, and you can end up with your giant and scary epidemic curve. And if you cast your mind back to February and March, there was a lot of discussion about these giant epidemics. So something else happened to me. When I initially made this slide, I had the population to be 4 million people of my community of interest. That's because I didn't realize there are actually 5 million people living in BC. I think it had gone up a bit. And I now use 5 for this. But anyway, it was 4 million people back then. I said, well, what if the R0's 2.5? I took some typical incubation and infectious period parameters, didn't think about it too much. And you see that within 3 or 4 months, you have hundreds of thousands of people in the infectious group. And you probably remember that from the Imperial College group, seeing these kinds of things, which changed policy in the UK and also in the US. And my friend Joe Wu, who's at Hong Kong University, also had a paper which came out in Lancet right at the end of January, and these are his versions of these big, scary curves. And he was already talking about trying to reduce mobility of people, trying to reduce transmissibility in the hope of flattening these curves. And we'll talk a little more about that in just a second. Okay, so I just want to use this graph, which is just the SEIR model with some fairly arbitrary parameters, just to point out something which is reasonably obvious. So at the peak of the graph, when you hit the peak here, that the derivative of the cumulative incidence, the number of people who've ever been infected, it has to be equal to 1. Or in other words, each infected person here is infecting exactly one more person. Before the peak, they were able to infect more, and that's how the number of infected people was growing. After the peak, they're infecting less than one person, and so the infected population is declining. But right at the peak, the effective reproductive number is exactly equal to 1. Well, we also call this the herd immunity threshold. So this is the threshold where if I was able to just arbitrarily decree that the epidemic would stop anywhere after the point where herd immunity is reached, and then I tried to restart the epidemic by bringing some people in who are infectious, the epidemic would not restart because we have reached herd immunity. So the definition of herd immunity is it's the number of people that must become immune by vaccination or by infection to prevent the onset of an epidemic. And of course, this is ignoring the possibility that people who've been infected might be able to get infected again, and we're starting to see that, but I don't think it's that big of a deal on the whole. So herd immunity gets reached at this point, and this is a very important concept in epidemiology. And this also has the effect that, in a sense, all of the infections that happen on the downslope are sort of wasted, in a sense. If you've reached this point, then these people really didn't need to get infected. If you could just have stopped the epidemic at some point before that, these people didn't really need to be infected. Okay, we can also do some nice math, and I'm going to kind of skim over this slide, but if you take this model, you can basically integrate it in a certain way. The quick studies will be able to read through this very rapidly, but we can solve this for s plus e plus I derivative, and we can integrate that. We can see that this integral we can do on the left, it's easy enough. So we get s infinity here minus the number of susceptible people at the beginning, which is approximately n. And then on the right side, I can rewrite I using my first equation from SEIR. I get a logarithmic derivative, I integrate. And then I can basically write that in the end, R naught times the fraction of people who never become infected, sorry, 1 minus the fraction of people who never become infected is equal to minus the log of the fraction of people who never become infected. And this is just a fact, and you can do this kind of calculation for a lot of models of this type. And it's probably better shown as a picture. So the final size of my epidemic, the fraction of people who become infected during this full epidemic, unmitigated epidemic, is this blue curve as a function of the R naught. And so you can make decisions. So if you want 70% of your population to be infected, then your R naught should be equal to about 1.7. If you want 30%, then it should be equal to about 1.2. And this is also related to the concept called flatten the curve, which was talked about a lot in March and April. And the idea here is if you have an epidemic with some kind of R naught, then if we can reduce the R naught, then we can replace, for example, this orange epidemic with this blue epidemic. And not only does the peak number of people infected, which is what you're worried about for hospital capacity, not only does that peak get a lot lower, but also the integral, the area under this curve, also gets a lot smaller according to that final size calculation that I just showed you, or just skimmed over. Although in my 80% of British Columbia example, even in the R naught equals 1.2, at some point next year, we would be finding a very high number of people would require hospitalization if, very roughly speaking, 10% of the cases required hospitalization, which might be just a little bit on the high side. Okay, and then this is also, I think, obvious, is suppose you have a scenario where R0 was equal to 2.5 for a while, and then you were able to bring in some public health measures such as social physical distancing or things like this, and reduce the effective R0 down to something below 1, and then we see exponential decay, because when R0 is less than 1, you'll definitely have decay. But then after a while, we get tired of this and we just go back to normal life. Well, you kind of end up with more or less the same number of people infected. Your reduction in mortality and morbidity is really not very big. And so I think everybody knows this, that if you're going to start physical distancing, you're going to have to be ready to keep that going for a long time, or find some other strategy. So possible strategies being vaccination or targeted test and tracing. If you want to do targeted test and tracing, it's probably wise to not have too many people to test and trace at any one time. So you want to turn that on at a low ebb of the epidemic. Okay, so just changing gears a little bit now. So I've kind of gone through Epidemiology 101. That's at least a month of problems and homework when I teach it. So I can fill in the gaps in the homework exercises. I'm joking. Just changing gears a little bit, let's have a look at what's happened here in British Columbia, which is a little different than what happened in Texas, but I think some of the lessons, some of the story can kind of be the same. What we saw in British Columbia through January and February was really very occasional. Almost all of these cases were linked to international travel. Somewhere around the mid to late February, there were some travelers returning from Iran, I believe, who I think that the virus had actually spread from Europe to Iran and then came back to British Columbia. And those travelers were able to generate some spread, which in particular went into old people's home and started to lead to deaths beginning in BC around the beginning of March. And suddenly, over the first 2 weeks of March, we had this big ramp up in the numbers of cases that were being detected. And these numbers were high. It felt like uncontrolled spread. Fortunately for us, the school's 2-week spring break started right around March 14th. My wife hurriedly came back from Atlanta, where she was visiting her family on this day, and my kids were home. We had spring break, and then the kids basically didn't go back to school after that. They had just a few days in late June in the end, and then we're on holiday again. So essentially, physical distancing started around the time of this darker band here, and the story by mid-April was that it was pretty clear that physical distancing in British Columbia was working pretty well. So by the end of February, a working group had been formed with British Columbia Center for Disease Control, and I'm going to present a model that largely came out of Caroline Colline's work, and it's nothing fancy, but it does the job quite well, as I hope to show you. So essentially, what we have here is we have an S E1, E2, R model with a quarantine compartment that's sort of optional. You can hop over the quarantine. You'll see that there's 2 tracks in this model. That's because people can either be distancing or not distancing. Sorry, I got that the wrong way around. Not distancing is the top line, and the D's are the distancing compartments. There are 2 exposed classes. This gives us a little bit better map of the transmission kernel that I showed you before. But basically, there's 2 kinds of people. There's the ones who, for whatever reason, maybe they're medical personnel or they have other issues. You know, if the schools had stayed open, these might have been teachers. There are people who are not able to distance, and then there are people who are like me. Suddenly, I'm working from home every day and trying to avoid going to the grocery store. So I'm a distancer. I'm down here. And just an important thing when you start to break your population up into these kinds of things is that it's not just a fraction of distances that comes in. You actually get the square of the fraction of distances in quite a few of your equations. I'm not going to show the equations, but the square starts to show up. And that's because imagine that we have, you know, people who are green and people who are pink. And the pink people tend to go out more. So these are more maybe the medical personnel or the essential workers in the model. Well, when the pink people go out, who are they going to find? They're going to find more pink people than green people. So you're going to see, if you see your epidemic, it's to some degree more going to be more in the pink or in the upper row of this model than in the lower row. Okay. So armed with this and some parameter estimates and some thought, we fit this to, this plot is up to mid-April. We fit this to the case counts, and you can see the case counts are quite noisy. We fit this in a Bayesian framework, and the two dots there correspond to the dark period. This is essentially the school spring break, which is when we started to bring in physical distancing. We brought it in on a ramp rather than an abrupt cutoff, but it doesn't make a whole lot of difference. And essentially, by mid-April, we were starting to get quite a nice prediction that we had gone through a phase where R naught was bigger than 1, and then essentially R naught had become less than 1 following the physical distancing, plus a delay for the fact that it takes some time to go from being infected to being transmissive. Okay, and if we look just at one of the posteriors of the fit here, if you look at what the distancing people are doing, we find a pretty robust posterior suggesting somewhere in the range of 80% of the contacts have been removed by the physical distancing policy in BC. Okay. So, you know, you can see from the data, we could see from the model that the physical and social distancing kind of worked in March, April, and May, based on, and this is all based on case counts, and I'll come back to this a little bit in a minute. But we could kind of estimate from case counts around 80% contact reduction in March, April, and that basically declined as time went on. The government started to lift a lot of the restrictions and people started to return to something closer to everyday life. And so we estimated that the contact reduction was more like 40% by the end of June, and I'll show in a minute that it's well, I'll show in the next slide that it's gotten worse. And you can read this on medRxiv. It's accepted in PLOS Computational Biology. Yeah, but I would say we're not the only group in the world that did this. This idea of allowing the social distancing to vary over time, and we built up a picture of the epidemic in BC. Okay. So unfortunately, if you look at this plot, this is just number of cases in BC, and this is coming almost up to today, although there's always a bit of a fall off because not all of the cases get reported right away and things like this. So these are cases by symptom onset date, and you can see we had a period of several, well, really over 2 months where essentially the case counts were extremely low. I think a lot of people were starting to think that the disease might be effectively eliminated in BC, and we were feeling pretty optimistic. Unfortunately, this didn't continue, and we now actually have larger case counts every day than we did right back at the beginning. And so if you continue to use the model that I just kind of summarized, and this is a slide from the Chief Public Health Officer's presentation last week, what you'll see is that by allowing yourself to vary the contact rate for the distancing people between, say, 50% and 80%, you can get different projections of this. This is actually not up to the end of August. This is only up to August 10th, but you can get different projections of what would happen for the rest of August. So if people's contact rate was 50%, we would see things kind of level off and go down. That's what we want. On the other hand, if it's more like 80%, then well, the model still fits pretty well, and then it continues to climb, right? So they use these kind of pictures to try to explain to people what may happen if the contact rate persists at a high level. And the story here has largely been, well, I'll show you, but it's largely been around young people going out and getting in big groups, and the contact tracers are tracing thousands of people. This has been really the story of the last month or so. And I feel so old when I say young people, because I used to be a young person. But anyway, so yeah, but I want to show you really some interesting things about this, which is that the numbers of new cases, right? We had this initial rise in March and April, then the long sort of low period, and then the building cases again. But the number of hospitalizations has really, in the second wave, and I almost hesitate to call it a second wave because it's really a continuation of the first wave, but in this recent period, the numbers of hospitalizations and deaths have been very low. Now, most of the deaths in the early phase were among people over 85, and the remainder of those deaths were among people who were over 60. And so it makes sense to ask, okay, was there a difference in the age distribution of infection between the early period and the late period? And that's exactly what there was. I apologize, this graph's a little bit busy, but I'll highlight the light green here. This is people 20 to 30, and you can see they weren't certainly weren't overrepresented in the early phase, but they're overrepresented now. The next group is 30 to 40, the next group is 40 to 50, and then 50 to 60. And the elderly people are staying reasonably low, although with some concerning trends here. So if you have a picture in your mind where elderly people suffer morbidity and mortality at much higher rates, then this makes perfect sense, and it's essentially being driven by younger groups. Yeah, okay. So yeah, as I say here, trends in infections versus hospitalizations versus deaths, they show that there's complexity underlying this that isn't being captured properly by a simple model of the kind I showed you, where you sort of have two compartments. Although I still think that model has its uses for understanding the sort of averaged trends and this heterogeneity. I think an important point I want to emphasize is that testing data is always incomplete because not everybody who is infected or infectious will necessarily be tested. In British Columbia in March and April, the policy was actually, if you weren't feeling particularly sick and you didn't have any reason to think that you might be infected, you weren't allowed to be tested. There weren't enough tests available. Now there are plenty of tests available. And so it's possible also that we actually have a better representation of the second wave than we did of the first wave, and in particular of those younger people. So maybe there were younger people infected back in March, but they weren't being tested at a high rate. But this means there's a question, and especially thinking about herd immunity, which is what I want to do next, is to assess, are we near to herd immunity? We need to have a better sense of how many people have ever been infected, or indeed how many people are infected today. And then the second thing I just wanted to mention is in our big picture model, we can say 60% contact reduction or 40% contact reduction, but that doesn't really help people actually decide what to do as their activities. And that's still a decision that has to be made by the public health people in their messaging around what's safe and what isn't safe for today. And there's no direct linkage between reopening bars or reopening barbers versus levels of contact. And I think this is a general problem of trying to relate mathematical modeling of this nature back to actual practical policy. Okay, but back to herd immunity. So as I previously said, herd immunity is this concept that you either vaccinate or allow people to be, or have people be infected somehow so that the R0 is effectively becomes less than 1. Okay, I want to make 3 comments about herd immunity. Okay, the first comment is, we actually don't have a great estimate of how many people have been infected. So I've got 2 kinds of things to think about here. So the natural thing you would imagine is to do case counts and serosurveys. And I put that on the left, and that's in Times New Roman because that's a very serious font. And this is what serious people would be doing. They'd be out performing large-scale population testing. And this sounds easy, except for the tests have appreciable false positive and negative rates. And in British Columbia, where we haven't had a very big epidemic, we've only had 200 deaths, to give you a sense of the scale. They put quite a bit of effort into serosurveys for antibodies, and they really haven't managed to get above the noise in the test. So you have to be careful about the statistics. And in fact, I think one of the pieces of data I've seen, they actually, purely from that data, they can't actually exclude 0 in their survey, zero cases in their survey. The other thing, which came out maybe more early in the epidemic, is that you have to be extremely careful around sampling, especially if there are costs and benefits to the people you want to sample from. So there was a well-publicized serology study in California, and it turned out that the PI's friends were largely represented in the blood that had been drawn. And the other thing was that there were considerable benefits to knowing that you've had coronavirus, because you can then not be so worried about it. So I'm always concerned when I read about these things about the possibility of test-seeking behavior. You have to construct your study in a way that's unbiased. And this has not always been carefully done. On the right side, in Comic New Sans, which is a less serious font, because I don't take this calculation particularly seriously, but I still think it's worth doing. If you a pretty reliable Danish study showed that the overall of around, I think it was around 10,000 blood donors aged 18 to 70, showed that the overall infection fatality rate was probably around 0.1%. The exact number is not especially important because this is a rough calculation. Up to May 13th, there were 23 deaths in adults 18 to 70 in BC. And so my estimate for the number of infections in adults in BC up to May 13th was 23,000. This was largely borne out by the antibody test, because the antibody test wasn't able to really resolve sub 2% differences in how many people had been infected. And so this led to an estimate of the underreporting factor. It's somewhere in the range of, I said 1 to 10 times. I always think it's about 5 to 10 times, but yeah. Okay. Second thing about herd immunity, irrespective of the fact that it's going to be difficult to actually measure this, is that there's quite a body of theory on this, which says that population heterogeneity is very important. And I'll try to illustrate this with these two graphs. So the left graph is a community where everybody is connected to everybody else. Everybody contacts everybody else. So that's the equivalent of the well-mixed SEIR type assumptions. But on the right side, I've got a model with the same number of people, but you can see that 5 people are kind of hubs. So those are high contact individuals, and then you've got sort of low contact individuals, depicted around them. Okay, so imagine you want to vaccinate to prevent some kind of epidemic process happening on this graph. Well, the random vaccination threshold is the same for both of these. So if you randomly vaccinate, say 3 people, then you're going to end up with essentially the same early dynamics, or the same probability of an epidemic going across your graph. But if you have an epidemic that's running, then it induces this sort of natural herd immunity, and it happens much quicker on the right-hand graph. And the reason for that is simple. Imagine that your infection process starts here with this person infected. Almost certainly one of the first people they're going to infect is going to, actually I think it is certain because of how I drew the graph, but is going to be this high contact person here. Okay, well that's bad, right? Because you get this rapid spread, zoom, zoom, zoom. But that person's now wiped out, they're immune, right? So you're actually killing off your high contact individuals more quickly. And so you can actually achieve herd immunity with fewer infections. And then if you want me to prevent spread of a virus by vaccinating people, I can vaccinate smart on the right side and just vaccinate those people, the high contact people, the medical personnel, the essential workers. Not back on the left, I can't do that. I just have essentially vaccinated random. And these ideas can be built out into mathematical models. And there's already, even over the last 10 to 15 years, there's been sort of an industry of modelers trying to work on these questions. And I would draw your attention especially to Gabriela Gomez with an S, who's published quite a lot on this and has some I think some of the most interesting and best ideas about this. I will skip a slide, but to make my third point, which is that it's also going to be difficult to infer what's going on, because people, irrespective of what the government is telling them to do, people are doing social distancing, wearing masks, and this is changing the contact structure, and in a heterogeneous way. I have a comment about this, which is essentially people are kind of smart. If I was a 75-year-old person with an underlying condition like my dad, I would go to great lengths to not become infected right now. But as me, I go to moderate lengths, and then I spend some time talking to my son and his friends, trying to encourage them to go to any lengths to I'm exaggerating, they're very responsible. I shouldn't say that out loud, but there's variation, and that variation reflects a number of things, and maybe the economists might even be better equipped to look at this as sort of a game theoretic problem. Okay. So the naive estimate for R0 is 2.5 about random vaccination, should be around 60% coverage. Gabriela Gomez in her preprints has been arguing that 10 or 20% might be enough. My issue with this is essentially it's been very difficult to measure and establish where you are, and also to disentangle things that may look like herd immunity in terms of decelerating infection rates, which may actually be caused by effects such as people not being stupid. It is true, however, that because we have a disease which is where the bad effects are largely skewed towards elderly people, if those elderly people also are able to have low social activity and self-isolate themselves, then you will see reduced overall morbidity and mortality. And this is a good thing, but it also makes it more complicated to study. Okay, I think I have just a minute or two left. Okay, so we built back in 2009, 2010 with some colleagues, Babak and Jessica, who are pictured here, we built a model for BC, which has multiple age groups and has some people being highly active in social life or work life, and they have lots of contacts, some people don't. And we can use this now to study questions around coronavirus on the assumption that not much changed over the last 10 years. One thing I wanted to show in just about 4 or 5 slides, but this is the bit that's going to get cut off, is the vaccination efficacy and deployment. And the highlight here is essentially we used this model. We simulated an early epidemic, then we kind of stop things and we say, okay, we're going to vaccinate, and then we're going to see what happens, and we generate contour plots as a function of vaccine uptake and vaccine efficacy. And they're not very surprising. If you get a lot of uptake or a lot of efficacy of your vaccine, things are good and not too many people get infected, not too many people die. And it's bad if you have a bad vaccine and hardly anyone takes it. It makes sense. Unsurprising results, right? What I think is more interesting, though, is when you start to break things out by age. So a lot of vaccines are relatively ineffective in older age groups. About 10 years ago, I was going to Africa and some family members were with me who were in their 60s. I got a yellow fever shot. They didn't, because yellow fever shot just basically doesn't work in people who are over 60. So if that's a factor, then now plotting the vaccine efficacy in people over 65 and the vaccine efficacy in everybody else, we start to see that mortality is actually is more controlled by the efficacy in the over 65s, even though the efficacy in the under 65s will be largely controlling the transmission to those people. Okay. Although you can mitigate that by having the people over 65 continually socially distance themselves, but then you have to ask questions about the social costs of this. The bottom line being that vaccine efficacy in those older age groups is really a critical thing, and it's important that the trials that are going on right now actually look at this point and make sure they recruit sufficient people in those age groups, make sure they have durable antibody responses, and so on and so forth. We also looked at smart deployment in this model, priority deployment to elderly people, priority deployment to high contact people. And we found that in the best case scenario, we could reduce the mortality by about 40%. Okay, getting tired and we're almost done. Lots of challenges coming up over the next 6 to 12 months. I think particularly interesting is facilities. Schools and universities. Universities are the most complex thing I can think of because people live there, people work there, people study there in big groups. The groups are dynamically changing. Understanding spread at the university level, I think, is very challenging and interesting. Schools a little bit less so because, especially in elementary, they are relatively compartmental. Trying to understand how the transmission networks have changed in the face of this epidemic, and related to that, changes in testing patterns. If you have a lot of young people testing, all of a sudden you're going to see different things than you might have seen if you just left them alone and they hadn't been being tested. Yeah, and then because today is World Overdose Day, I can't remember what it's called, but the largest the day when we remember people who've died of accidental drug overdoses. Just want to show you one plot from BC, which is contrasting in blue COVID-19 deaths and in red overdose deaths. And it's fairly clear from this plot that the overdose deaths is really the public health concern that we should be focused on in BC. And the COVID-19, I'm glad we focused on it and kept those blue bars small. But one thing I'm planning to do over the next year is try to return to the overdose response modeling that I was working on previously, with the goal of trying to understand how we can improve matters here. And I don't think there's any. It's completely clear that COVID has affected the usual routes of supply of opioids to people who are addicted to opioid drugs, and has led to them having less ability to accurately gauge dose and also be exposed to contaminants. Anyway, all models are wrong, some models are useful, and a good model does not fit all the data because some of the data is wrong, and especially with real-time data, the second one is important. And especially when talking to general audiences, we have to always remember the first one. But I think it's important to keep modeling and keep telling people about it. And with that, and I apologize for going a few minutes over, I am done. Thanks.
Oh, thank you very much, Dan. We really appreciate it. I really wish that Zoom was capable of doing applause properly, but I'm pretty sure you can be assured that people are applauding right now. So we really appreciate this very much. Let's open the floor up to questions. If you have a question, please type speak in the chat window and we'll get to you in the order in which those requests arise. All right, so I see that Krista has a question. Let me unmute your mic, Krista, and you can ask your question. Go ahead, Krista.
Hi, Dan. That was really, really helpful and super useful. So I really appreciate the talk. One thing that I guess there probably wasn't much time for was the discussion of comorbidities. One of the criticisms that people who don't want to social distance or wear masks often use is to say that the deadliness of this thing is way overblown because everyone that died would have died anyway of something they already had. And that the fact that they had COVID at the same time means the person at the hospital records it as a COVID death when in fact it was a pneumonia death or a diabetes death or something like that. And I'm wondering if the structure of the quote unquote second wave with the young people mostly catching it can tell us anything about whether that's true or not.
Yeah, I have. So the two words you've got to look at related to this question, and I have crazy relatives on Facebook too, just in case if that's motivating any of this, but is excess mortality. Ultimately, we have to look at the excess mortality. The problem with that, with looking at numbers of deaths compared to the usual level of deaths, is that the social distancing, physical distancing, and people, things like people being afraid to go to the hospital or having, minor surgeries have been delayed, these kinds of things, does have an impact on people's health and may be responsible for some small amount of the excess mortality. I totally agree with you, though. I think you're making a valuable point that looking at excess mortality in an age-structured way will hopefully bring a lot of this out. It also, the other thing I always think is, well, life is a pre-existing condition, right? So everyone's got to die of something. And when I'm 84 and I have emphysema or whatever I'm suffering from, I would still be unhappy to die 2 years earlier than expected from COVID. I would still hope that, and also Dr. Tedros, the WHO guy, right? He made a nice quote today or yesterday that, it's not really acceptable to just allow old people to die. This is not how we're supposed to function as societies. And yeah, there is a lot of nonsense been talked about this disease. And but on the other hand, the electronic age allows nice things to happen too, like talking to you. And it's a double-edged sword, as with so many things. Yeah. Anyway, sorry, I'm rambling a little bit now, but yeah, I think that age breakdowns of excess mortality will be really useful information. I don't have that to hand, and honestly, in BC, the total COVID mortality in anyone under 60 is minimal. I think I'm still younger than anyone who's died of COVID in BC. So that will continue for some period. Yeah.
Thank you.
Okay. Yeah, thank you, Krista. Sully, you have a question? I'm going to ask you to unmute. That might or might not have worked.
Yes, did that work?
Yes, that did. Perfect.
Yes. Well, first of all, thank you for giving your presentation. I enjoyed it. I'm very interested in the whole argument between why do we have to do anything because Sweden didn't do anything, so and they're fine or whatever. That argument's very frustrating to me because obviously they had a much larger mortality rate anyway. It seems like that's sort of a lazy argument just to say, like, I heard somebody say this and now I'm just going to repeat it. Can you tell me why Sweden didn't have problems, if that's actually the truth, or yeah, and how can we relate that to the US?
Yeah, a few months ago, I just decided I'd really had it with Sweden. And I told a few Swedish friends this, and they agreed. They felt their country was being used sort of inappropriately as kind of an arguing point. But I mean, more seriously, right? The per 100,000 death rate in Sweden, I think, is very comparable with the US. And then people say, well, okay, so why did we bother doing anything? Because Sweden didn't. But that's really, I think, simplifying things. I think it's oversimplifying the question. Sweden did do things. That's the first thing. Is from my contacts with Swedes on the ground, life did not proceed as usual in Sweden. Now, they did not have a draconian lockdown, but people, especially again older people, were taking care of themselves. It's this business that, you know, the government can say one thing, but you know, older people know they're at risk, and they knew they were at risk from the experience in Italy and New York and things, and so they did to some degree take care of themselves. A lot of the mortality in Sweden, additionally, has been old people's home mortality, which is terrible, and it's because they didn't take proper precautions around the old people's home, which is something we're also guilty of in Canada. I haven't looked into this specifically, but I suspect the fraction of old people home mortality is quite high in Canada as it is in Sweden. So this tells you, with a high fraction in old people home, that the fraction of mortality in broader society is probably lower than it has been in the US. But the main thing I always think is it doesn't matter what the restrictions are that are implemented. You know, South Africa closed its liquor stores. We never closed our liquor stores. You could still go and buy beer here, which I think was an important thing. It doesn't matter which rules are put in place. It's how that affects actual transmission. So transmission, you know, we're still grappling with the questions of what drives transmission, being within 6 feet of people for long periods. How some people seem to be much more transmissive than others. All of these questions, right? But stepping back from that, it's how did people's actual behavior modulate the transmission of the disease versus it's not what the rules were that were put in place. That's not the question. Sorry, I feel like I slightly lost the plot on that answer, but the point is without going out and measuring what people are actually doing, I don't know that you can infer what they were actually doing from what the government told them to do. Yeah.
Okay.
Oh yeah, sorry, can I say one more thing? Sorry.
Oh, sure, of course.
And also, I don't believe anywhere in North America has done anything which we could really consider a lockdown. Even the California shelter-in-place thing has all kinds of exemptions, right? Lockdown to me means you have to stay home, right? and we were never anywhere close to that, as far as I know.
Yeah, thank you for answering that question. So it seems more like the answer to somebody saying that Sweden argument would be, yeah, they didn't necessarily do something through the government, and that's why a lot of people died. Similar to the US, even though they did take their own precautions, their mortality rate and infection rate was still quite high.
Yeah, I think that's fair. The US, as in so many things, seems to be taking, the discussion here is unique to the US as well a little bit, right? And I think it's become unfortunate, really tragically, it's become tied up with politics in the US, which I think is not helpful no matter what side of the argument you're on. I mean, I think there are legitimate arguments in favor of not having a strict lockdown, you know, because there will be large unintended consequences of that. However, I feel like people who bring up Sweden, maybe a few months ago it was okay, but now I'm starting to think they're just sort of intentionally deceptive, you know.
Yeah, no, thanks, Dan. All right, one last question, lightning round. So maybe like 30 seconds to a minute. This was a private question that was sent to me by Chris Hayward on chat. What's the sort of minimum population size that these models need to be considered reliable enough to either fit the data or project the data forward some amount?
Great question. It'll depend on the R naught, and the size of the fluctuations will be something like the square root, as they usually are for these kinds of systems. I'm drawing a blank. I would say 500 to 1,000 people. I will admit, a guilty thing that I did was early in the epidemic. We worked on some prison settings, and we applied the model, even though we kind of knew that it probably wasn't quite right, but we were just trying to get some stuff out.
Okay. Yeah, so, and that's 500 infected people that you would need to have minimum before the model becomes reliable, or 500 in your general population?
Oh, sorry, 500 to 1,000. But if the R naught's 2.5 or 3, then you're going to have a large enough number of infected people.
Okay.
Yeah.
Okay.
I mean, you run into the problem of the infection dies out due to stochastic events early on, but modulo that, I think that would be reasonable.
Okay. Well, thank you very much, Dan. I'm going to try one experiment here at the end. I'm going to try to give you some applause as we close out the colloquium. All right, so let's see. Oh, never mind. Okay. If you unshare your screen, I can try to give you some applause here as we close out. But I don't want to be too much of a pain here.
No.
All right, I'm curious to see if this even works. So here we go. Let's see if you can hear this.
Yeah, I can hear it.
Okay.
Thanks so much. Yeah.
Excellent. Yeah, no, thank you very much. And I'll be in touch with you after the colloquium for some follow-up things, but thank you everybody for participating. And our next seminar is in 2 weeks. We're going to take the Labor Day off from those events, but from colloquia, but after that, we're going to resume the series with a seminar. Okay. Thanks everybody. Take care. Stay well, stay safe.